3. And we are doing what conic section right now? Ellipses. Now hold on, where have we been? Section 10.1 was what conic section, which is actually a degenerate? Lines. So we've talked about lines, which is a degenerate, which is kind of weird, but we talked about lines. The new things with lines, anybody remember something new about lines we talked about in 10.1? Of? Well, that's his name, but angle of, there's a name. No. Does anybody know a blank plane? No. Going up a steep incline. There you go. Inclination. Woo! I was trying so hard. An inclined plane. So maybe that's a physics term. Angle of inclination. Incline. Theta. Yes. Equals. No, that wasn't the formula. It was m equals. Why was m in there? Slope. Slope equals what of theta? Tangent. Okay, so in section 10.1, we talked about inclination, incline, and how there's an angle to lines, and how that incline, his tangent, or its tangent, wait, inclines always have to be what kind of angles?
Positive.
Positive, good. So inclines, angles of inclination, the tangents equal to slope. Slope, tangents, that was the whole thing. There was also some weird formula with M1s and M2s. You guys remember that one? Angle between lines? Okay, just reminding you it's there, because remember, by the time we get to the end of chapter 10 or chapter 10a, we're going to be like overwhelmed with formulas, forget stuff. So the more we remember it, the better we'll be. Section 10.2. Now, Priscilla, what conic were we on? Parabolas. So, good job, that one. Parabolas. But we've done parabolas this year also. So what was new with parabolas? Go find the yellow box for parabolas, 10.2. The yellow box for parabolas and what we did with it are going to help us with the yellow box for ellipses and what we're going to do with that. So what's new with parabolas? The focus, the directrix. There was only one focus, right? Because parabolas only have one curve. So let's do a weird one. Let's do a facing right one. Okay? Where's the vertex? The farthest edge of the curvature. I'm going to put it that way. But you're right. It's in the middle of the branches, right? But do you guys see it's the farthest right of the curvature? Ah, is that the way that goes? Oh, yeah, because L makes left, right? Okay, so the farthest left of the curvature. What letters usually stand for the vertex? You can do V, but I mean as far as the point. H and K. Good. Then you guys said that the focus was new, right? Where's always, 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 where's the focus? To the right. No, it could be up or down or to the left. Said, yeah, P over and inside the parabola or inside the curvature, right? So P over to the focus. In this one it's over. Sometimes it's up, sometimes it's down. But P distance away, right? And in this one, since it's headed to the right, does anybody just by context of the problem know what this point would look like?
H plus P.
You're adding, good, you're adding a P, and you're adding a P to the X value, right? To the horizontal coordinate. So H plus P comma K. Okay. And then what was the other direction? Yeah, the directrix is the exact same distance, but the other way, which is going to be kind of awkward. It's going to go through everything. And does it make sense? That would be X equals H minus P, the other direction? Okay. But in the yellow box, yes, it's important to know the vertex and the focus and the directrix. But isn't it important to know standard forms? Didn't we use that tons in homework 10.2 and in examples? So which standard form tends to go with this one or would go with this one? The y. No, y equals x squared. That's like a normal up-down one. No, not y equals x squared. Y minus k squared one, which is weird, but it goes on the left, right? Now, usually in parabolas, we'd say something like a, but we don't. What do we say? 4p. Because this p is the same distance to the focus and then the opposite way to the directrix, right? So we needed to take what was whatever coefficient was in front off to the side, set it equal to 4p, solve for p. Did that in homework, did that in examples. I would highlight it every time. You guys remember that? Okay. And then we have x minus h. Now, there is another standard form if it was an up-down, yada, yada, yada. But, oh, pause. Would the coefficient in this one be positive or negative? Positive, because the focus is in the positive direction. Hopefully our lives are the same. So coming back, I tripped. Yellow box for ellipses. Super important for us to finish this section today and to understand how to make ellipses, identify key characteristics of ellipses, and be able to take or be given key characteristics and generalize and be able to find the ellipse. Anyway, very similar to parabolas, except the equations are different, yeah? What do the equations look kind of like? X minus h squared plus y. No, not parabolas. Okay, parabolas, yes, because there's an h and a k and at least one squared. Parabolas only have one squared, right? Ellipses have, similar to, what'd you say, Matthew? Circle, right? X minus h squared plus y minus k squared equals r squared. I was going to do this whole visualization today, but just because time is short, it's chapel. Let's get through all the examples, and if there's time, I'll show you where an ellipse comes from. But we have an h and k, but this time h and k is not the outer edge of the curvature, the vertex. In this one, h and k is the center, like we're used to a circle anyway, right? Okay. Is there really that much difference as to how to find h, how to find k between the two? No. Wait, is there really much of a difference at all between these two? What's the only thing that changes? Yeah, just where they are. They're still both squared. They're still in the denominator. They're both going to be numbers. So what's the difference between who's A and who's B if they're both numbers and they're both squareds? A is the major. What does that mean? Look at it. What's true? It's the majority or the bigger one, longer one, right? The bigger one, longer one. Radius is only half the distance. Do you guys know what the whole thing would be called? Yeah. The book doesn't use the word diameter. I like the idea. They just call it the axis. They just call it the entire length of the axis. Because this one, the axis doesn't really go outside. We don't really talk about x equals or y equals for the axes in this one, not the same as we talk about like directrix and axis of revolution on the parabola. So I know it's weird if we're calling this a major radius. Wouldn't we call this the major diameter? But we don't. So if you want to make a quick note to yourself, if they ever say major axis, what they're actually talking about is the entire length, which is going to be helpful for a couple homework problems. I think even for the example you were working on just now. The axis is the whole thing, like a diameter. I know it's awkward, but it works. How many foci do we have for an ellipse? Where are they? Along the major or the minor, looking at the pictures? Always along the major. Always along the major. Why would there be two foci? Wasn't it inside the curvature? So isn't it inside the curvature? And inside the curvature? Well, hold on. If the foci are inside the curvature, then couldn't there be vertices outside the, or on the outer edge of the? Yeah. So we have vertices, we have foci, but they're always along the major axis. We have vertices, we have foci, always along the major axis. And the only other weird thing is, well, how do we get to the focus? P for parabola, but what do we do for ellipses? C, there it is. Okay, I don't know. But C. But who's C? We have to go looking for him the exact same way we went looking for, well, not the exact same way. We can't go to a parabola formula. So how are we going to find C? Did you guys make a note of this? Highlight this, star this, make it important? So let's go to, well, let's go to the example you guys are working on. So give me something. Give me anything. Ooh. Somebody thinks C is important. C equals 2. I like it because what's the distance from the center to the focus? 2. Either direction. Good. C equals 2. Give me something else. Matthew's thinking about which standard form. He says the a squared goes first because he sees everything horizontally apart. He sees the major axis as being under the x. Do you guys agree? Check out your pictures. It's one that's squished in the horizontal direction. He's also noticing that it was h plus or minus c, and then for the vertices, h plus or minus a. So he's looking at those formulas and kind of working backwards, right? Sort of like you're adding to the x, so therefore. Yeah, good. Good. So now that we've picked a standard form, can anybody tell me how to plug in? I'll show you the spaces that we need to plug in. You guys see them? Give me something. Who's H? Mm-hmm. Who's K? That's all from looking at the center, right? What am I missing next? Okay. Oh, A is the x one. So how far out in the x direction? You guys agree? Is it 3? Yep. So how far in the y direction? Yeah, that's what I would guess. How could we make sure we're right? Isn't there a formula for this guy that says that c squared equals?
A squared minus B squared.
So if a is 3, 3 squared would be 9. And if b is 2, 2 squared is 4.
T squared.
Uh-oh. Am I in some trouble? Oh, I need to square root both sides. What did they tell me C was?
2.
Now what is 5? Is it close to 2?
Yeah.
But does that mean I've made a mistake somewhere? Yeah. So here's the dilemma. It looks like 2. Doesn't it look like 2? Ish. Got in trouble. Got in trouble. If you guys look here, do you see how it's super precise between the x value of 2 along the major for the major radius, and then they put this little line to show me it's exactly at 3, 4, 5. So you guys were totally right. Between 2 and 5 is a distance of 3. But did they carry this one across?
No.
Ooh. So does it look kind of like 1, 2-ish?
Yeah.
But it's not exactly hitting at the 3. And how do I know that? Because this is not that. So hold on. What should I maybe have done instead? Instead of saying this is 2, maybe I should have left it blank and done what? Taken what you knew and say 4 is equal to 9 minus who squared? C has to be 2, so C squared has to be 4. A has to be, look at that, it's clearly between 2 and 5. You're right, it's 3. A is 3, I should say. 3 squared is 9. So then I'm going to end up with who's the root 5? Not C. B is. Oh, yeah. That's nice, Jason, because he's like, oh, go throw it in over here. But when you square it, root 5 squared isn't that just 5?
Yep.
And 3 squared is 9. With a little plus in between. Bless you. Guess what? That's standard form. Yay, done. But could it look like anything else ever? Some of you on Friday, and I think it was with this example, right before we left, you were like, wait, you would leave it like that? Remember how parabolas we would leave in a weird way too, because like the standard form is a little different now, so we would leave it with like stuff squared and we would leave it with stuff over here. Sometimes you're going to leave it like this. So it's not a bad idea. If it is an odd, go back, check in the back of the book. And this is standard form. That's fine. You could stop. But sometimes, just sometimes, they might say something about and simplify. So let me show you what that would be. For the one on Friday, it's already in your notes. I don't think you need to go back and change it unless you want to. But for the one on Friday, guys, what would get rid of the 4 and the 9? Yeah, 36, right? I mean, maybe something bigger, but 36 would. So couldn't I technically take both sides and say times 36 and times 36? Everything's still balanced if I'm multiplying on both sides, right?
Yep.
And what would happen when you distribute? What's 36 over 4? 9 times x squared plus what's 36 over 9? 4, and 4 times 4? That's another way of writing it. Or technically, if we went back to the, that was a long time ago, to the standard form of a conic, which standard form of a line is that awkward ax plus by is c, that awkward one. I need to go to the double-naped cone. Where is he? He's back here somewhere. Or if I was to do standard form of a conic, I could move it all to one side with a 0 over there at the end, which wouldn't really change. This one, all I would do is say, 9x squared plus 16y squared minus 36. Is that one good? Yeah, he's probably the best. But is that one also true? Yeah. That one? Mm-hmm. So I guess we could do the same thing with yours. So kiddos, if they did want you to simplify or get rid of the fractions, or you were looking at a multiple choice answer, or you were trying to take it further, what would you multiply both sides by? I think 45 is probably better, yeah? Okay, so if we do 45 on one side, sorry, pretend it's the times on the outside. Just in case you're like, do you stop there? I would say, yeah, I would say stop there for homework. But if for any reason you ever did have to keep going, what's 45 over 9? And then 45 over 5? But what would make this one harder to like fully, 45 times 1 is 45. Ah, yes, but I'm a little worried that you would have done it illegally, Jason, because you can't distribute first. PEMDAS, not multiplication first, but, and how do you square it? FOIL. Careful, don't just bring the squared in. Illegal, killing puppies. Let's not go back to that. You have to FOIL x minus 2 times x minus 2, y minus 1 times y minus 1, FOIL, and then distribute, and then combine like terms, and then... Can we just stop? Is that okay? Notes. You have a good example in your notes. You now have a good example in the back of your homework spiral. That was a little bit harder. But I want to do one last example. Maybe two. Having to do with what we just said. You would have to FOIL and distribute and combine and let's stop. What other types of examples can they give you? You guys remember from section 10.2? They can give you clues and you sketch and you try to figure out, which was what these last two examples were. They can give you equations and have you sketch. They could give you sketches and have you do standard form equations, or they could give you the nastiest form of the conic. Now, hold on, wait. Matthew was like, what's eccentricity? We haven't even... Okay, pause. Sorry. There's one last little detail. There's one last little detail. If you guys started writing the example, you could leave like maybe 5 or 6 lines and then write this. But as you saw in the directions, there was one little detail that we left out. Eccentricity. Eccentricity, doesn't it kind of look like eccentric? We could try to think of some way of remembering eccentricity with the word eccentric. What's the word eccentric mean? Like if you were to read it in a story or something. Not eccentric. You're think the mathematical. Eccentricity is exactly how you would say this. But if someone was eccentric, I don't think you would call them eccentric. Never heard that one before. Oh, come on. In English, if you were reading a story and someone was eccentric.
Wealthy.
No? What? No?
They're just like high status.
No? Formal? No?
Bougie.
It's a little bit closer.
Yeah.
Not quite right, though. Because bougie these days, I don't know, I think it's somewhat of a positive term.
It wasn't?
Bougie kind of is. Like, you could be mocking them, but at the same time, it's usually on like the higher end of things, right? If you're bougie.
Isn't that what eccentric is? Proud?
No? This is interesting. Hold on. Let me go look up Google definition. We can look at it together. Not from my experience. It's usually more of a negative connotation. You guys know denotation versus connotation? So maybe the connotation in my mind, maybe the older use of it.
Oh, isn't it just deviate from?
Yeah, but I mean as far as like a person, if you were to... Okay, yeah, it's exactly what I thought. You guys, not a person.
Is that eccentricity means how it not looks like a circle?
Joe's still going back to math and trying to... I thought you guys would have the English form of it so much better.
Circle, and the smaller it is.
I hear you, Joe.
Squished.
Yeah. So what Joe's saying is like, oh, it's something off. Okay, Joe, thank you. But we're trying to think about the English term of it right now. I thought it would help people's mathematical understanding. But Joe's just going from the math and saying like, hey, from what I can tell, I think eccentricity has to do with something about how squished it is, how off it is, how apart from or deviated from a normal circle it is. And that's kind of how it works with people too. It's ironic I'm going from math to English. But if someone is eccentric, usually it's a person who is unconventional or slightly strange. It's not so much about having money or wealth or prestige or being kind of bougie. It's more of just they're usually kind of off. Like one of those, like, I don't know. When I was growing up in Santa Maria, there was a purple lady. She had a purple car, she had purple hair, she wore purple clothes, and she even dyed her dog purple. She was eccentric. She was very eccentric. It was like, huh, okay. Yeah.
I think it's just whenever we hear it, it's always in relation to wealth. What's his name?
Like the weird rich people?
Yeah.
I guess so.
Always called like an eccentric.
Yeah, and you could. I just didn't think about how you guys wouldn't have read like the older stories where it's not necessarily Tony Stark is like a cool Iron Man Avenger. That's interesting. Like the meaning of the word has changed in your minds just because of who you associate it with. Yeah, eccentric was usually like, they're the weird, like, in the house that I wouldn't ever really go trick-or-treat at. Like, it was usually a negative connotation. But, I mean, and some people would say that about Tony Stark, like, Iron Man, man, he's abrasive, blah, blah, blah. Like, but, interesting. Anyway, and you guys can see the synonyms, and I don't think you would tie most of these to, like, rich people. Abnormal, irregular, odd, queer, strange, peculiar. Not in the way that you guys think. Anyway. Lame. Words change. Weird, bizarre, off-center, outlandish, freakish, extraordinary. Like, I get, you guys are thinking the extraordinary kind of part or the outlandish kind of part, but really it's usually like in old stories or even just newer stories, it's usually a pretty negative term. But anyway, all of that to say, now that we have at least the same, what I was thinking of eccentric, it's how far off from the norm. You could think of it as in that sense, how far off from the norm. And it's not necessarily negative as far as how elliptical or how squished or how far off an ellipse is from a circle, but it does kind of work. It does kind of work. That's so funny. Totally thought that was an easy question. Anyway, guess not. I'll have to like poll all my alumni and see where the meaning changed as far as years. Anyway. Eccentric, eccentricity, how far off an ellipse is from a circle. So a circle has a perfect radius, right? The major and the minor are exactly the same. A is equal to B, so both radii would be the same when you're plugging into standard form. Squared over a squared plus y minus k squared over a squared. You wouldn't need two letters, just one. There wouldn't be a major and a minor, it would be the exact same. So how do you find eccentricity? C over A. C is that little dude, and if I were you, I would write yourself a reminder because all these letters start to get confusing. C squared equals A squared minus B squared. That C. C being the distance from the center to the foci. And if you guys notice, check it. If the foci are really close to the center, really far from the curvature, isn't that still pretty circular, right? So then C is little, and so if you plug in a little c, the eccentricity is small. Oh, so it's not that far off. Now, if eccentricity goes between 0 and 1, the closer it is to 0, the more circular it is. Because if the eccentricity was 0, how far off would the foci be from the center? They wouldn't be. There would be no foci because there would be no ellipse because it would be a circle. So if the eccentricity was 0, that's a circle. And if the eccentricity is 1, guess what? That's a line. Because if the foci are all the way pulled out, that thing has been completely flattened, and you have a, hi, thanks. You have a line instead of, you would have a line instead of, instead of a curve. So the closer to 1 it is, 5, 6, 7 tenths. 9 twelfths, that can be reduced. Anyway, anything that's greater than a half is very distorted. And then anything that is like 1/3, 1/4, 1/5, 1 whatever, 10th, getting more and more and more and more circular. Okay, so now that we know what eccentricity is, let's go back to our example. Because at least we know, okay, that's HK, that's the V, that's the little foci, the 2 points on either side of the center, and then that's how squished it is, or how far off from a circle it is. Now we can read the directions. Whew, we have to do the math. But we've done this type of problem multiple times with parabolas. Can you guys maybe even just give me a direction to head as far as where to start? Oh, you guys think? X is here, Y is there. Okay, let's organize stuff. So, X stuff. 9x squared, and the 50 minus, good. Carry the minus, the subtraction. Minus 54x. The Y stuff. Careful. Do you see how I'm leaving a space?
There's something.
Because for parabolas, wouldn't we leave a space right here for the constant term? Okay, so down here, 4y squared plus 40y, what are you going to do? Leave another space. Because I need my, think about it, x minus h has to be a perfect square, so he needs a special third term. And y minus k is a squared, so another perfect square that needs another third term. And I can move, thanks Joe, but hold on, we haven't finished this yet, right? Hold on. Let's stay focused on the task. Focus. Anyway, where you direct your attention. Curvature. Anyway, so if I have 2 blanks, it's because I'm going to put... But let's come back now that it's all set up to what Joe said. Joe, don't say anything. Does anybody, did anyone register what he was saying? He said, oh, we can... Yeah, he talked about the 9. Factor out. Why would we want to factor out the 9? If we go back to our yellow box really fast, is there any room for anything other than 1 being with x and y? These can be different numbers. Those can be different numbers. That has to be a 1. There's no A in front or B in front or C. Okay, well, those letters are used elsewhere, but there is no room for coefficients in front. So the struggle is right now, does this 9 belong, or can he stay? Well, if he can't stay, then, and he never can in completing the square, what are we going to do with him? Before we actually do the blank, we're going to factor out the 9. Which they were so nice to you because they made the 9 come out nicely from both. What else can we pull out? 4. Uh-oh. Don't forget they're out there, guys. The 4 and the 9, don't forget they're out there. We haven't added anything in yet, so we're still kind of waiting over here as far as this side. But now it's time to figure out what goes in the blank. What is the process called of taking? Yeah, we factored out. Good. And now what do we need to do in order to make this a perfect square trinomial that we can factor? And what's this whole process called? Complete the square. We're trying to complete the perfect square trinomial. Literally, it's what we're doing. We're completing this perfect square trinomial. So, yeah, you guys were telling me take the middle, cut it in half, and square it. I think you're starting to complete the square at least a little bit better. Isn't that 3 squared, which is 9? Sorry, -3, but -3 times -3, +9. How about this one? What goes in the blank? Nice. It's not a huge, complicated process. Just split that 10 into 5 and 5 and say, I need u squared. Which we could go ahead and factor to be x minus 3. Do you guys see how that's the guy that was in the parenthesis before the squared? Minus 3 is what was half of that, and minus 3 is what's the square root of that. Plus 4 times, what's this going to be? Careful. Yeah. No, you're good, you're good. So easy to do. Even the calc kids do it. Y plus 5 squared. But I can't show what's over here because what have I not done yet? So what's bad if I add 9 and 25, which is 34, and get a negative 3? Why is that horrible? Someone help Priscilla out. She's struggling. If I add the 9 and 24, oh wait, that's 33. I can't even add. But even then, guys, why is it bad to have a negative 4? So I can't fill in blanks and I can't add. But why is it still bad? Thank you. Oh, I did it right in my head and then I wrote it wrong. Thank you, thank you. That'd be 34 and that'd be negative 3. Why is this bad? How do I get a 1? Divide by negatives and I have negatives? Are there negatives in any of those standard forms? So I did something wrong. Did I do? No, that was right, that was right, that was right, that was right. Why did I tell you not to forget what you pulled out? Because when you put a 9, you're not putting a 9. What are you putting? You're adding a greatness of, or an additional 81. If I add 9, I haven't balanced anything. He's still way stronger. I need an 81 to keep it balanced. And what else do I need? 100. So I know those numbers don't match. They're not the exact same, but they're still completing the square because when I added this 25, he was really 100, and that was really 81. And now this also makes sense mathematically because I should have a positive number. If you ever get a negative, it's probably a degenerate. Ah, those degenerates. All right, 181 minus 37 is 150, 144. Well, that's nice because 144 has a square root. Wait, we're not supposed to be square rooting. What are we supposed to be doing? But that's not standard form. We have to find the center and the vertices and the foci and the eccentricity, Joe. How do we get it to be 1? No, my standard form, you guys can check it out. Look at the yellow box. Don't I need equals 1?
Yes.
So subtract 143.
No.
Divide by 144. What you do to 1, you do to everybody, just to make it nice and even. We're distributing it ultimately when we divide by 144 and then bringing it into both terms. Joe did say something about 36, but he was kind of a step ahead of us. Now we have equals 1, just like standard form says. But wait, it's a circle because it's 12 and 12. No, who do we have up top? Does 9 go into 144? And the answer is yes. And it goes in 16 times. And 4 goes into 144? 36 times. Hold on. What have we now gotten? What form is this? Standard form of an ellipse with h's and k's and a's after you square root and b's after you square root. That will help you fill in all of your clues. Guys, you guys go ahead and go. I'm going to finish up this problem just by saying, here's my center, here's my focus, foci, here are my vertices, plugging into my formula. But you guys got it. This was the hardest problem of the section. Bye. You got this. Tackle ellipses for tomorrow. So my center, H, K, my foci and my vertices.
I have my sections as well because I was absent.
Yeah, you were absent. Thanks, bud. Bye, Joe. I'll take it. Thank you. Bye, sir. See you later. Welcome. Ooh. The major is right here with the y term. So my major radius is going to be 6. Square rooting that 36. And my minor radius is going to be 4. So horizontally, I'm going to go 1, 2, 3, 4. And 1, 2, 3, 4. And vertically, I'm going to go 1, 2, 3, 4, 5, 6. And then 1, 2, 3, 4, 5, 6. If I connect them in somewhat of an even curve, this one's always a little bit pointier than I would like. There's my ellipse, and I can go ahead and find my vertices by taking my HK of 3, negative 5, and say I need to add to the y's to get to my next one. So 3, 1, and subtract from my y's to get to the other one. So that'd be 3 and negative 11 because that major radius is 6. So I have 3, comma, negative 5. Uh-oh, hold on. My foci isn't adding a radius, it's adding C. We'll come back to that. My vertices, though, are adding the major radius, which gets us to the points of, well, the ones I just identified, but that's okay. Of 3, 1, and 3, negative 11. Yeah, I'm just going to put you in the back. Do you have a phone on you? No. Okay.
Hi, Misty. How was your weekend?
It was good, buddy. We need our C for this one. So C squared is going to equal A squared minus B squared. So C squared is going to equal 20. So C is going to equal 2 rad 5. All you do is throw that in that spot. And I don't know what that is. That's a nasty square root. So I'm going to go ahead and just write it and call it good. My center, my foci, my vertices. The last step that we just haven't done quite yet is my eccentricity, but we know my C of 2 rad 5. We know my A of 6. Reduce that puppy. You can see mathematically how off from the norm or off from the circle they would call this ellipse. It looks pretty squishy to me, but so we did a few examples, talked about eccentricity, and got you to homework. Hopefully that helps you for what you got to do tonight, and I'll see you tomorrow. Bye. All right, cool.